This is video number 6 in our series on the derivative, and we're going to talk about the graphical interpretation of the derivative and also the second derivative, which you have not heard of yet. So if you look at the top here, you see our function 2x cubed minus 9x squared minus 24x plus 10, which is the black graph here on my screen, which I'm going to label f of x. Then you will see right below the original function, the first derivative, f prime of x equals 6x squared minus 18x minus 24, which is this blue parabola on the screen. Now I want you to notice, remember that the derivative tells us the slope of the tangent line to any point on the graph, or the instantaneous rate of change of any point on the graph of f of x. So when f of x has a positive slope, we expect the first derivative to be positive. When f of x has a negative slope, the first derivative should be negative. So let's look at where the first derivative is positive. In other words, y is positive for the first derivative. So this little red section indicates a place where the first derivative is positive, and also when x is greater than 4, the first derivative is positive. Now let's look at values of f of x where x is less than 1. So if we're looking at the section of the graph from -1 to the left, we notice that these are all values where f of x has a positive slope. So here we have positive y for the derivative function, positive slope. And those are for all values where x is less than -1. Actually not equal to, but x is less than -1. Now in between -1 and 4, so -1 is less than x is less than 4, notice that my values of the derivative function are all negative. So we have negative values for y. Notice also that the original function has negative slope for those same values. So if we look at anything less than x is 4 and anything greater than x being -1, we have negative slope and we have negative y values. Then if we look to the right where x is greater than 4, then notice once again positive y values for the derivative function and positive slope. So you can see where negative values for the slope here correspond to negative y values. Positive values for slope here and here correspond to positive y values in the derivative function. And what about the zeros? The zeros of the derivative function corresponds to the maximum and minimum points, the vertices of the original graph. And this is all summarized down here. You might want to write this on your paper. You can pause the video to do that. I'm not going to just sit here and wait for you to write, but you can pause. The first derivative, f prime of x, tells us the slope at any point on the original function f of x. When f prime of x is greater than 0, the slope of f of x is positive. When f prime of x is less than 0, remember that's our y value of our derivative function, the slope of f of x is negative. When f prime of x equals 0, f of x has an extreme point. Okay, now let's look at what happens when we add the second derivative in. So the black line is still f of x. The blue parabola is still f prime of x. But now we have a red line, which is f double prime of x, the second derivative. Now let's look at the top. The way you get the second derivative is just to take the derivative of the first derivative. So 6x squared minus 18x minus 24, if I take the derivative of that using the power rule, I get 12x minus 18. Once again, stepping down 1 degree, from third degree, then to second degree, then to first degree. So now we see that the second derivative is a line. Now what does the line tell us exactly? Oops, I lost my graph there. What does the line tell us exactly? It turns out that the line tells us what's called the inflection point. The inflection point tells us where the rate of change is the maximum. The inflection point is where the graph of f of x changes from being concave down to being concave up. So I'm going to use the highlighter here. From here to here, the graph is concave down. And then from here to here, the graph is concave up. Right at the point where the rate of change is minimum is where the slope is the steepest. Okay? So this is called a point of inflection. Point of inflection. It is the maximum rate of change of f of x. Now you might think, why does that correspond then with a minimum value for the first derivative? Well, think about the fact that the maximum rate of change is in the negative direction. We have negative slope here, so this is the biggest negative slope that I can get. Remember that the first derivative tells me the slope of every point on the original graph. So the extreme point of the first derivative tells me when my slope is changing at the most extreme rate, when it has the biggest slope, in other words. In this case, it is the biggest negative slope. Now, what happens on the third derivative graph? Notice if we look at that same point, when the second derivative, the third graph, the second derivative, when the second derivative is 0, that would tell us the extreme point of the first derivative, which tells us the point of inflection of the original graph. That tells us the maximum rate of change. It also tells us when the graph divides from being concave up to concave down. So when I have negative values for my second derivative graph, so f prime of x less than 0, then it tells me f of x is concave down. When I have f prime of x greater than 0, f double prime of x, the second derivative, greater than 0, that corresponds to f of x being concave up. Concave up. So that would be anything to the right of 1, looks like about 1.5. So these are all the concave down areas. These are all the concave up areas. When f prime of x equals 0, that tells me the point of inflection on my original graph where the maximum rate of change occurs. So all of these particular values are useful in real life when you're trying to analyze a function. You're trying to find out if this function represented something in real life, then knowing when it's at its maximum, its minimum, when the rate of change is the maximum are all valuable things to know about the function. And the second derivative tells us where that maximum rate of change is. And it tells us about the concavity of the graph. So you can, using the first and second derivative, you can tell a lot of things about the original polynomial and be able to draw it. And that's something you'll be doing a lot of in calculus, and we're just kind of introducing that here.